Hello and welcome to the first of our premium videos. Right, we're going to be talking about context-free grammar throughout this whole period, or rather context-free languages throughout this whole period, or for the first half of this module, and then we'll shift on to other languages that the likes of context-sensitive and so on. But first, we need to understand what context-free grammar are, right? So we need to take a step back and look at where we've come. So far up until this point, we have done regular languages, right? So with these regular languages, we've found out how they behave. We have found the rules that lead to their formation. We have found the machines that accept them. We discussed the properties of regular languages, right? So if you, at this point in time, are not familiar with what I'm talking about, you need to take a pause and revisit your content from the module COS3701. Right. So now, the next step is to look at context-free languages. Right. What we see from here is that context-free languages is much a bigger language than regular languages. And then by virtue of that, regular languages are a subset of context-free languages, which means all regular languages are context-free languages. This is a phenomenon that we're going to explore later on as we move. Right, so this is the focus for now. We're going to be focusing on context-free languages. Right. So a context-free grammar, right, is just a notation that is used for describing languages. Right, so it is a notation. Right? Then we find that it is much more powerful than a regular language, right, or regular expressions, or any of the tools associated with regular languages, because it has got more languages than regular, right? But it still cannot define all possible languages, right? So it is, we see from this previous slide that yes, we have got context-free, but we've got context-sensitive and unrestricted, right? So though it is bigger than regular, it is not the biggest, right? It is useful for nested structures, like parentheses in programming. So nested to have a function inside a function, right? So we'll see how that all plays out when we talk of nested, how that all plays out when we move on. So regular expressions were a little bit sequential, right? So it was saying do this part, then do this part, then do this part, then do that part, right? So regular expressions, for example, a use of a regular expression, then we will look at uses for context-free languages when we see it happening. But for regular expressions, right, we know that an email address is got, for example, my email address is kuda@ivtutor.com, ivtutor.com, right? All email addresses have got a similar structure, right? The structure of an email address is known. So all email addresses are going to have something, then then something, then dot, then something. Right. So when you go on a website and you want to sign up for something, or they ask you for your email address, and it has got that red asterisk there, usually if they do email validation, what are they looking for? They are looking for these two critical points, right? And they give you permission to put some characters here, some characters there, and some characters there. Meaning you can write a regular expression for this. Right? So here you can have 0 to 9, right? You can also have A to Z. You can also have capital A to Z, right? And so forth. So these are all the allowed characters. You can specify the allowed characters, and over here and over there. So this is an example of a regular expression that is telling us how to give the language of or the rules for forming the language called email address. right? So that was regular languages. Now we are talking of context-free languages, and we are saying they're useful for nested structures, right? So we can have functions inside a function using context-free grammar. All right, but we'll explore that a little bit later on. That was just an introductory comment. All right, so now let's define context-free languages. A context-free grammar, let's start there, is defined as a collection of three things, right? You need an alphabet of letters called terminals, right? Alphabet, so you prefer to use the symbol sigma. An alphabet sigma of letters called terminals, from which we are going to make strings that will be the words of a language. From which we are going to make strings that will be the words of a language. All right, so let's get one thing straight. So we have an alphabet. We should describe when we talked of regular expressions. The alphabet or the alphabet letters are the ones that are used in the final word of any language. Right. So the other name, or the name that we're going to call them in this case, is called terminals, right? From the word terminate, right? You terminate. When you get there, you cannot proceed any further. Then number two, a set of symbols called non-terminals, one of which is called S, right? We have got a symbol or a set of symbols, and we've got a specific symbol, special symbol that we have called S, which represents start here. So this set of symbols called non-terminals is usually represented by capital letters T, S, R, V, right? S is reserved for the starting non-terminal, which represents start here. Right. So we now have two sets, one of the alphabet of input letters, number two of a set of symbols. So the first one is defined as letters, right? On number one, we're given letters. Here we're now being given symbols. So symbol, from the word symbolize, we are saying, you see that this symbol can be replaced by a terminal. This non-terminal can be replaced by a terminal because the goal is to have all terminals at the end. Right. So this is just a set of symbols. So number three, a finite set of productions of the form one non-terminal going to a string of finite terminals and or non-terminals. Right. So the relationship between the letters and the symbols, or the non-terminals and the terminals, is given by a rule, right, or a set of rules which are called productions. Right. So productions, in fact, are responsible for generating all the words in a language. Right. I then gave an example here. Right. We have got a non-terminal S which represents start here. Right. So a rule, you would have S goes to AA. This is a production. This is a production. And this production says S can be replaced by AA. Right. So a production can be, we say a non-terminal can go to a string of terminals, or we can have a non-terminal going to a mixture of terminals and non-terminals, or we can have a non-terminal going to only non-terminals. So all these three scenarios are allowed. Right. So that is the definition of a context-free grammar. All right. Now, given a context-free grammar, right, a context-free grammar will generate words, right, or a set of strings, right? So the set of strings of terminals that can be produced from the start symbol S using production, the substitution, is called a context-free language. Right. So there are two key points to take home from them. Number one, anything that belongs into a language needs to originate from S. So it needs to have started from S. Otherwise, it is not a word in the language. So if I take a step back, so AB is not a word in the language because it is being developed from X. AA is a word in the language because it is being developed from S, which is the starting point. Right. So that is the difference between S and the other non-terminals. The next take-home point is that CFGs generate a language. And CFGs themselves are a rule for generating a language. So they then be in, they look like, or they are to CF context-free languages what regular expressions were to regular languages. All right. So that is it. That is what context-free languages are. That is what a context-free grammar is. And I'll see you in the next video.